it's a bad timing to make up the class in the evening. And the students like to have a party, okay, have a lot of girlfriends to deal with, that's why. All right, never mind, this is the only break I have. Tomorrow morning I have to entertain those guys from the government, including those guys from the NSTC and DOD, this kind of stuff. All right, so let's get to it. We'll take a break around 7:45, all right, in about 5 to 10 minutes, and then we'll close the entire session around 9. All right, okay, good. Oh, this is what we were on Monday. So we emphasize that, well, I myself, I emphasize that, okay, everything in IC design can be pre-estimated before you go to the software. And however, due to the convenience of the software, the machines, well, students always, do the homework and the practice and the projects in the last minute before the deadline. That is why. But the bottom line is, okay, for those students, let me tell you what. I have a lot of friends and students already working in IC design houses. They don't have that kind of luxury that we have. They don't have enough license numbers for every IC design to use. For example, the focal tech, they have like over 100, maybe 200 IC designers. But the license that they have to do the simulation, maybe it's just a 10 or 20. So before they go to the design, they have to use a hand calculation or those non-licensed file to do the estimation before they go to the real design. That's rule number one in their company. Rule number two is that they always emphasize, okay, they always emphasize one thing. They have to plug in all the parasitics, including the capacitance, resistance, and even conductance in the pre-layout simulation before they do the layout. That's how they do, because that will save a lot of pain. Because when you find out all the numbers you get before and after the layout simulation are so different, you have a big trouble to explain to your supervisors, your managers, your colleagues to what the hell is going on. Okay, this happened in my lab, in my students too often. For example, some students from India, they just like, well, a lot of them, not just from India. They just use the software, do the layout. Before the layout, they run the schematic simulations. And then suddenly they find out, for example, the delay could be two times difference between the one that they get before the layout and the one that they get in after the layout. So I asked them why there is such a big difference. They could not answer. The only answer I got from them is that, well, this is what I got from the software. Okay, sir, you like it, you take it. If you don't like it, there's nothing I can do. So what I'm supposed to do, right? Well, this is the attitude problem. So one day when you go to the industry, from the day one, you'll be paid with full salary. And those managers, they are not like professors. Okay, we can tolerate that students make mistakes in the school. But when you are paid by full salary, for example, $2 million per year, you don't have that kind of margin that you have in the school. You have very limited margin to make mistakes, okay, in a company. That's why I'm telling you this, all right? So, okay, this is just something that I want to bring to your attention, okay? Run the simulations is one thing. But before you run a simulation, it is even better for you to do the estimation before you run the software, okay? And this is what we talk about on Monday. So these are just typical numbers because this is a process you're going to use in this course, 180. Okay, it's a 6-metal process. And we have a metal 1, 2, 3. Basically, we have 6 layers of metals. Okay, remember these rules. This is very important. Metal 1 is specially, okay, needed inside the cell. And outside the cell, okay, interconnect between the cells. Please use the metal 2 and the 3. okay, because you need a lot of metal wires to travel between different cells so that they can come up with a bigger one, okay, big subsystems. For example, you design an adder cell. Then you need an 8-bit, then you have to cascade 8 adder cells together. Then you need metal 2 to 3 to help you to do the connection between these cells. And then number 4 to 5, they are meant for bigger or higher levels, right? So for example, you have adders, then you have other logic operations, then we call that ALU, arithmetic and logic units. You want to combine them together. Okay, please use a 4 and a 5. Okay, this is well, ALU is the first chip I designed when I was a student. Okay, that's interconnect between units as for critical signals. The top layer, okay, the one on the top for everybody, okay, is metal 6. And metal 6 is a layer to be connected to outside world, okay, to be connected to outside world. So that this metal is especially for the pads. Pads is a connection to the external world. Okay, pads then go to the bond wires, metal wires, then go to the lead frame. Then they are, they are meant for clock signal. They are meant for power, ground, and one more. One more that is missing from the text, which is called reset. Put it down. Because every digital circuit, you got to have a reset. Before you do the operation, before you invoke any operation, you got to reset all the flip-flops. Because every digital circuit got to have a flip-flop. If you don't reset your flip-flops at the initialization stage, the D flip-flop will be locked in the middle of nowhere. You got big X. You don't have a 0, then a 1. You cannot assume the D flip-flop will give you a ground. That's impossible. Okay, you cannot assume that it will give you a high VDD. That's impossible. It will be trapped somewhere in the middle. So you have to reset it before you use it. Okay, so there's something missing in the textbook. That is a reset. Reset, power, ground, and the clock. These are 4 major signals carried by a metal 6. Is that clear? Oops, what the hell is going on? All right, sorry. Okay, and these are the numbers for the resistance, or for the MOS transistors. Okay, there are several materials that can give you resistance. Up to now, we found out that we can use a polysilicon, we can use a metal, we can use diffusion, and the last one is active devices. That is a transistor. Transistor means that from time to time, okay, this is a P, this is an N, okay? This is P, this is an N. And technically speaking, if they are fully activated, so of course there will be a current comes down from the power supply and all the way down to the ground. So because this is made of semiconductor materials, you cannot assume there is no resistance. It's impossible. Okay? So basically, we have an equivalent resistance, which is called the RP, or over there, or EQP, equivalent. And this one, similarly, will have REQN. That is equivalent MOS transistor resistance over there. So if you check this out, okay, unfortunately, okay, this resistance they are not constants. They are not. Okay, the constants of this MOS-based transistor depend on the voltage, because this is why. See? Now check this out. This is something you have to remember. This is 0.18. That's the process you use. All right? So when the power supply is only half, that's 5 kilo, basically. If the 3/4 of VDD is about 8, Okay, and for the P process, there's 16 and 22. 16 and 22. So if you don't give it a full power supply, you cannot assume that it has a very good, reliable resistance. So, so the REQ depends on the operating voltages here. So for your process, for our process in this course, that's over here, 0.18, and we use 1.8 VDD. And basically you have a 10K ohm for the end device, okay? And this is for the minima size, with the minima width and the minima length. And for the PMOS, it's about 28. Okay, that's about 3 times difference. 10 and 28. Okay, keep that in mind. So it's very easy to remember. Because as in this class, all the students are new, beginners. So we don't ask you to remember all these numbers. One day, some of you will become very good or excellent designers. Some of you would like to use, for example, half the VDD to carry out a so-called low power operation. Fine, be my guest. The lower the voltage, you can find out that the higher the resistance. Okay? The lower the voltage, the higher the resistance. That is when the voltage of the power supply goes low, the operation of your transistor will be slowed down, which is equivalent to the increase of the resistance. Okay, so as you can see, when the PMOS, the power supply drops to 0.3, the resistance is over 100 mega ohm. That's very close to it, open circuits. Okay, so these are numbers that if you have enough space in your brain, please try to remember this one, 10 to 28. Okay, that's for the minimum size, that's the resistance of minimum size PMOS and NMOS, respectively. Okay, so this is the the numbers that I encourage you to remember. Okay, so all the numbers that we have. Now we can take a look to check it out. What is the difference between these two layouts? Okay, the one on the top is a very typical transistor. See over here? Because we follow the rule, we follow what professors say, we use the minimal size so that it can work. And we have two contact over there. A contact is exact, so we cannot change the size. But here, we can change the size in the middle. This is the one that fits the minimal size. And the design of this one is that the different thinking. Because the space here, okay, the space here is automatically wasted. Why don't we just take advantage of that and cover them with all the diffusions so that we are going to have a wider transistor in this way. So right now, the first one is the feature size. Excuse me. So it's 2 lambda over 2 lambda. So the width is the same, the length is the same, they are both 2 lambda, minimum size. And this one, we don't mean to save this kind of small spaces. We fully use all of them, so the lambda, the width become 2 times larger, which is about 4 lambda. Then the Rn is dropped to 4, from 8 to 4. Okay. Then RP, if this is RP, drops from 22 to 11. Okay, it's not a 28. They use a 22. That's fine. Okay, just remember the number. So the 8 to 22 and 4 to 11. Okay, and these numbers are for the voltage not equal to 1.8. You can go back and check it out. It's here. They use this number A and 22. 8 and 22, okay? 3/4 of a VDD. All right, this is just a simple introduction of the resistance for every material that we use on the silicon. Now the next one is capacitance. capacitance is the one that the students hate most. Because capacitance is the one give a lot of trouble. It creates delays. It creates the, the interferences, a lot of bad things. But however, according to the basic of physics, that as long as we have two parallel conductors isolated with insulator, then we have a capacitor. So you cannot get away from that. All right, so since we cannot get rid of it, so we have to understand how to manipulate it. So this is a basic idea. It's called a wiring cap, wiring capacitor, all right? So we have two parallel conductors. The size is over there, okay? The size is defined by length with a small l, width a small w, and the height of that conductor is t, thickness. And the space between this conductor is called the TDI. And DI stands for the insulator, which is called a dielectrical. Dielectrical material, okay? It is an insulator, okay? No charge is allowed to pass. So this is the side view. So the top plate and the bottom plate, all right? And how to define the insulation of this dielectric, it depends on what kind of material you use. For the free space, we define the relative permittivity. It's very hard to pronounce it. Permittivity. We call that epsilon. R stands for relative. So free space is assumed to be single unit. It's a 1. Okay, free space is not air, it's free space. It's out there in the sky, in the cosmos, free space. Then we find out, after thousands of experiment and measurements, we found out the silicon is 11.7. Okay, I always tell the student to remember 12, it's easier. All right, 12. And the silicon dioxide, the one that we use on silicon, is 3.9. So I told my student to remember it's 4. It's easier. Okay, 12 and 4, 3 times. And if you use a nitride, expensive stuff, it's about 8. So it's 4, 8, and 12. Okay, if you have enough memory space in your brain, of course, you are welcome to remember this one. All right? No problem at all. So what is the unit for the single one over there, for the epsilon R? Is over here. This is a very long number, 8.8554 times 10 to the minus 14 power, farad over cm. Well, I myself, I cannot remember it after those years I spent in the campus. I was looking into the papers and try to find out. So the dielectric epsilon depends on the relative number times the absolute number. That is defined this way. Is that clear? So for the semiconductor devices that we use, which one we use is over here. 4, or you get 3.9 if you like. So 3.9 times this one, basically that's a constant. Okay, that's a constant. 3.9 times epsilon 0. Okay, so it's not too hard, right? Besides, it's a long number to remember. However, we have some enemy that we don't like. Okay, because even though that we give a very ideal assumption that two parallel plates, two parallel conductors, okay, and we assume that the electrical lines goes this way. That's how the capacitance is formed. But basically, the natural law tells us that there are always some bad guys. They don't follow the rules. We have some stray electrical lines get out of the boundary, but then they come back to the bottom plate. Okay, we call this a stray or fringe capacitor. Stray or fringe. So of course we can model that. That is how we model it. It's called the fringe. This is a direct capacitance, and this is a fringe. Okay? It does there. It does exist. It is there. You cannot take it away. Okay, it will go away just like the tax, okay, of our society. You always, well, you don't have to pay the tax right now. After you go to the real job, you will be taxed every year, and you hate it because, you know what? If I pay the tax to the government over 35 years, I still don't think that the government offer me a very good service. All right. All right, and then for the sideway, these are a pair of conductors. Of course, we have a crosstalk coupling. It is a capacitor called a lateral. Okay, this is about the area, this is fringe, and it's a lateral. Okay, they're always here. So fortunately, we have a lot of pioneers. They help us to find out the numbers. So for the ICINT, for widely spaced wires, okay, that's called the interference, the C times L. C equal to 0.1 if they are widely spaced, widely isolated. It'll become larger, okay, if they are placed very close. It's about a 0.15. That is how. And it's hard to remember these numbers. Don't worry, okay? Well, this is not the worst yet. Okay, the worst is it's coming. It is the capacitance generated, parasitic capacitance created or generated by the MOS transistor. How many capacitors are there? Just look at the screen. 1, 2, 3, 4, 5, 6. Total of 6 different capacitors. They are all called parasitic capacitors. Okay, it's hard to remember, but that's not hard. You just check the subscript. The first one is called the CGD. CGD. C stands for the capacitor. G means gate. D means drain. Right? O means overlapped. I will show you why it's called overlap. And CGB, sorry, gate to bulk, okay, to the big bulk. And gate to source, gate to drain, okay? This is very obvious to understand. And for the junction capacitors, where they are, okay, they show up, they exist around the diffusion area. It is a source to bulk and drain to bulk. So these two are called junction capacitors. They exist around the diffusion area, and they are always there. They won't go away, all right? So CSB and CDB. So let's check it out to see where they are. All right, this is how we define it. Okay, this is the gate. And since the polysilicon is a conductor, and we have a substrate over here, it's also a conductor. And the material in between is a zinc oxide. So of course, we are going to have a very big, relatively big capacitors, okay, existing between the gate and the bulk. That's the thing in the middle. And check this, okay, purple area. This area are meant to be source, either the source or the drain. And they are made of diffusion. But remember one thing, even though that we use iron implemented way to create these two areas, unfortunately, these guys, they don't follow the rule. Some of the extra material will be diffused under the gate. Under the gate. So apparently, we have a conductor over here. Of course, we are going to have a small, teeny, tiny capacitor. It is created by the overlapped area. So that's why it's called the CGDO, okay, and CGSO on the other side. So they are symmetric, okay, symmetric. All right, and this is for the source to bulk. It is a junction diode. Junction diode over here. Okay, junction diode over here. So these are all the capacitors, parasitic capacitors that we have. And this figure shows you the bird view from the top. Okay, apparently some of the material will be diffused under the channel, even though that we draw. Okay, we draw the devices on the layout. We have a very clear aligned cut, but in fact, after the fabrication, something will be diffused under the gate. That's why we have overlap. So the actual channel width is slightly shorter than what we draw in the layout editor. In the layout, this is what we draw with the L. But in fact, after fabrication, because of the diffusions on both sides, the real L is slightly shorter than the length that we draw about this difference. All right? So the channel length is not the same as we draw. And the CGSO and the CGDO can follow this rule. This is C oxide. This is a constant. We're going to explain it. And W is a width over here. And LD is the distance that diffusion travel into the channel. Okay, channel penetrate into the channel. It always exists. Okay, it won't go away. Just like in the society, no matter how hard you try, we all have bad guys. We don't assume that everybody in the society follow the laws regulated by the government. Okay, then let's go to see some lengthy and complicated equations. Okay, not only we have 6 different parasitic transistors, what even worse is that their capacitors are different in different, the capacitors are different in different modes of the transistors. Okay, if you, please recall that at the beginning of this course, we emphasize that transistor has 3 modes. Cutoff, right? It is totally shut off. Okay, nobody goes through. And then, after we increase the gate voltage, the transistor will be forced into linear region. That means it is slightly open, slightly turned on, that something is going under the channel. Then when we increase the voltage of the gate over a certain threshold, the transistor is fully turned on. It's called saturated, all right? So, unfortunately, these 6 parasitic transistors, their numbers are different in these 3 modes. Okay, this is for cutoff. When this cutoff, there is no CGS, no CGD, fine. And the gate to bulk is the W times L. This is the area times the constant, C oxide. And for the linear mode, that means that we have a channel already. So the CGS, the CGD, equal to half of this one, CGB over there. But because it is turned on, right now the channel is on, so there is no CGB, becomes 0. Okay, so different modes give you different, okay, capacitances. Well, that's hard. You're gonna say, Jesus, I have a limited memory brain memory. How the heck can I remember that? Don't panic. Okay, we are going to tell you the final conclusion, how to deal with that, because I have a poor memory as well. So this is what we're supposed to do in the estimation. Okay, and the figure on the top, okay, means that the channel is fully turned on, right into the saturation mode, so that the CGS equals to 2/3 of the C oxide times the area, and CGB and the CGD, they are both 0. So based on these phenomena, we have this table. This table is so lovely that you're going to love it, okay? So for the cutoff, for the linear, for the saturation. So we're going to have this one, this one, this one, all right? And for the CGB, CGS, and CGD. And linear for this one plus this two, okay? And for the saturation, it's 2/3 of this one plus CGSO. All right? So professor just said that you are going to give us a very convenient way to remember that. Okay? So this is the red box I want to show you. For the hand calculation, remember that we are designers. We always consider what? The worst case. We always consider the worst case. Okay? We are not the politicians. Those politicians, the governments always tell you good news. They won't tell you the bad news. Okay? But we are IC designers. We always consider the worst case. We want to make sure that our chips works no matter what kind of scenario, what kind of environment that this chip is used. That is why. So for hand calculations, it is safe to use these big numbers, WL, because this L is longer than the actual L, right? Okay, and this is a full capacitance, okay, and for gate capacitance CG, despite of operation mode. See that? Because this number is larger than everybody else in the table. It's larger than everybody in this table, so why don't you use it? So that is why. So from now on, no matter which mode this transistor is, we always consider that as long as we see that a transistor, you want to tell or estimate how big the capacitance is, use that one. W times L times a single unit capacitance. Then you are going to have a very safe estimation of, about the performance. Is that clear? Okay? If you like to remember everything, that's fine. Okay? But if you like to save your time and save your pain, okay, try this one. It's easier. W times L times C oxide. C oxide is a unit. We're going to find out what that is in the next few slides. Okay, now here we go. This is how we're going to find out. All right? So you check the table on the top. Which one you're looking at? 0.18. For the 0.18 process, okay, the zinc oxide is 4.1. Then we use a 4.1 plug into the equation for the smallest, unit size of the transistor with the epsilons. We find out a C oxide for that one equal to what? 1.33. 1.33 over there, okay, times the unit is microfarad over cm squared. Okay? Now, if you have a fixed size of lens, you check the row 3, COX times L. It's about, for the 0.18, it's about 2.4. All right, it's 2.4. Okay, check this one. C oxide, this is a single unit. This is the relative epsilon. This is the free space. 8.844 times 10 to the right is a very long number. And this is a relative number 3.9 over the thickness of this one. Okay, thickness of this one. So this is what we got. 0.45 microfarad over cm squared. Or you can remember that one as well. And this is for 0.35, which is no longer being used in Taiwan's university. This is one that you use. Okay, if you use the minimal size, 0.18, and the single gate capacitance, C oxide times A with a minimum number. So 1.33 is over there, see that? Okay, times blah, 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 this is 0.18 times 4 times 2 times of this one, 2 lambda, or times this one, and this is what you get. It's about 1 phantom farad, 0.86, you use 1 phantom farad. So minimal size, minima W, minima L. For the 0.18, for the single unit, you can assume that's 1 femtofarad. Or 0.86, you want to remember that's fine as well. Okay? So right now, see? Now we have this one. Then we also have what? Oops. That's femtofarad. Okay, and this is 22 or, I'm sorry, this is 10. Maybe 10 ohm, 10 k ohm. This is about a 28 k ohm. And these, they are the same, 0.86 femtofarad. We have R, we have C. So we can estimate how fast the charging is and how fast the discharging is. Okay, you don't have to go to run the software. You can have something in your mind, how fast that could be. That is how we do it. So for those students who always claim that they have a very high speed to me, in the past Monday lab meeting, one of the students announced or claimed that he has a voltage, create a voltage over megavolt. I say, you gotta be kidding me, man. Okay, if you can use an IC designed to have a megavolt in the internal node, you don't have to go to the graduate study to get a master degree. What you should do, you should take your circuit and go to the Thai power company, tell them, I solved the problem of your energy shortage because my chip can generate unlimited power. You see what I mean? When you run your simulation, you get a number that is not to be believable. So please double check your circuits. Okay? So we now understand how to estimate the resistance and as well as the capacitance. Of course, we can do the estimation of the delay. Okay? Well, sorry, a little bit fast. I forgot one thing, the junction capacitor. Remember when we mentioned the capacitance, besides the MOS, we also have another 2 junction capacitors. That is around the area of what? Of the diffusions. So the diffusion is sitting on both sides of the transistors. Okay, the size is W times Y. Y is the width of the diffusions. And we have a very lengthy diffusion cap equation over here. So no matter which one you use, drain and the source, they're all the same. Equal to the JA. A means the junction capacitance per micrometer square. That's the area. That is the bottom over here. Bottom over here, in the bottom plate. So this JA is the capacitance existing in the bottom plate of the diffusion. JP, P stands for the parameter. So it's on the what? On the walls of this area. So it's 2 times Y, 2 times W. It's around the area. So the diffusion cap is composed of these 2 terms, the bottom plate and the side walls. Okay, side walls is the peripheral capacitance. So this is the width of the diffusion area, that's the Y and it's W. And it's even more complicated, CJA or P, this is a constant. And this constant is made of J0 when there is 0 bias, no voltages around. Y minus Vj over Vb. Vj means the junction voltage across the border. JB is a constant built in the junction potential. And to the power minus ms, m's order. It's really complicated, all right? So no one likes it. We like real numbers. So how do we estimate it? Okay, now I'll give you some number to remember. So which one you like? You select this one. 166. That is the one you use. See, for hand calculation, you know the width of your transistor. The width of your diffusion. So you take the width to times the 1.66. Okay, you'll get the number over here, CGDS over here. 0.13, this is for the minimal size, and this one is for what? For the double size, for lambda. It's about 0.6, relatively big, because the one that created by the MOS is about 0.86, right? So they are close. So you cannot ignore the parasitics, okay, generated by the diffusion, because these numbers are close to the gate, the capacitance of gate. All right? So it's not hard. And the inductor. Well, inductor, we only have 2 slides for that because we are not going to develop or design the RF circuits in this course. If you guys are really interested in high frequency or high speed circuit design, you can select other courses. Well, in your senior year in the graduate school, some of the professors will cover that area. But how do we define the radio frequency area? Well, I'll give you some specific number. It's about 300 megahertz. Okay, if your circuit is over 300 megahertz, then we call that it's already into the area of radio frequency region, right? But according to my experience, most of the students, the beginners, they don't run the clock that high, so don't worry about it. But anyway, I just to let you know what happened. Okay, what happened? So the Faraday inductance law tells one thing. Okay, so when there is a sudden change of current direction, so di over dt times a constant L. This L does not mean the length; it means the inductor will be equal to the voltage drop that the current change created. So it's very scary. Why is it scary? Okay, and this is for units about 44 pH. P is 10 to the minus 12. It's very small. So most of the cases we don't care about it. But there is something very scary for your chip. It's called the ground bounce. What is that? This is your chip, and you have a lot of pad over here. Then, after you get the chip back, you will see that long, big metal wire is used to couple to the signal over here. Okay, and your chip is over here, can go here. And this one goes to your pin and goes with your board. This is a PCB board. Okay, but the board, this is your chip. Okay, and this is a bound wire. It is it's a metal, long, thick. Okay. When there is a current change, because based on the equation over there, okay, when there is a current change, okay, no matter it becomes large or small, it's vibrating or fluctuating. There is a voltage drops or voltage variation created by this kind of phenomenon. And if this happens at the ground, because we have a lot of ground pins, right? Ground pins around the chip, you will find out the ground voltage level in that chip will be fluctuated as well. It's called the ground bounce. It's just like this building was hit by an earthquake and the ground floor is shaking. Then you are not going to have a very clean signal inside of your core circuits. Okay, and if the current is very big, because the current change is big, the delta V will be big as well. Okay, and because this one is large N, large L. It's about a narrow Harry. Okay, maybe sometimes it's about a micro Harry. It's really large. Okay, that's what it's pico. So pico, we don't care. It's 10 to the minus 12. But it's a micro Harry or, or mini Harry. That's 10 to the 3 and 10 to the minus 3, 10 to the minus 6. And you times the current. And delta V will be very, very large. Sometimes it will be as large as around 0.3 to 0.5 volts. Okay, that could kill your signal. Okay, and there are two equations to specify, okay, when and how the inductance can be ignored. Okay, I don't invent these equations. I just copied from the textbook. Okay, over there. So the inductor effect is significant as long as this equation is satisfied. Okay, L is the length, inductance. So this is one. So, but this is two lengths to remember. Remember this one. Inductor is not important for any length. Okay, if the rise time is long enough. So the rise time is long enough. Okay, then we don't care. This is L. This is inductance, and this is resistance 4 times A over R. So basically, unless you are forcing to have a very sharp square wave output, most of the cases you can ignore, okay, the this factor. This factor, because we follow the bottom rule over there. Okay, so inductor is the last thing you should worry in this course. Okay, but however, it will be different if you take the RF circuit design. Okay, so we just drop the inductor. Right now, we focus on 2 factors: resistance and capacitance. Right now, we want to do the delay model. Okay, introduction. So this is meant for you to estimate your delay. Okay, there are 2 factors to to decide the performance, to determine the performance of a circuit, besides the logic correctness. Of course, before you go to the performance comparison, you got to make sure the logic operation of your circuit is correct. After that, you got to make sure that either you want to have a high-speed circuit or you want to have a low-power circuits. So there are 2 directions for your circuit research. So as I said to all my new graduate students, okay, if you have nothing to do, you don't know what to do the research in your career, okay, basically there are 2 directions, high-speed or low-power. Even better, you can make both happen simultaneously, but it's going to be hard. Because eventually the bottom line, physics limits told us, it's impossible to have a high-speed and low-power system. Check this out. Please raise your hand if you're a motorcycle. Okay, good. Okay, most of you have a motorcycle. Okay, tell me one thing. If you want to speed up your motorcycle, we got to save you a lot of oil. Impossible, right? You want to run it fast, the gas burns very fast. You're going to consume a lot of oil, a lot of gas, so that your motorcycle run fast, and the cop cannot catch you, right? Okay. If you run over light, but please do not do that. Okay. Run over the line from time to time. But just check your motorcycle, your car. I think every of your family has a car. You cannot, for a gas car, have a low power, okay, but high speed car, that's fine. And for the EV car, which is now very hot topic, I'm telling you the disaster is coming. What they are talking about? if you use the phone, like one, okay, you charge it and play the games at the same time. That is really bad to your phone because you play a game and you charge phone. That means you are charging the phone and discharging it on 10 minutes, and the battery will overheat. The higher the heat, the higher the temperature, okay, the shorter the battery life. Anyway, okay, according to my experience, I am the one who knows the trick to extend the battery of my phone to 6 years. Okay, up to 6 years. Okay. Well, the thing is, 6 years, the battery become a problem waste of the earth because it needs a lot of effort and energy to decompose the battery back to the elements so that it can be reused and recycled. Picture this. Okay, how many EV cars we have? It's getting more and more. It's coming. Okay, Tesla. Everybody likes to have Tesla. But you know that the cost structure of an EV car like Tesla, the battery cost almost occupy half the cost. And the life of that kind of battery pack, 3 to 5 years, that's all. Okay, the state of health will drop down to like 80% of the original storage capacity. 80%. And in fact, maybe 6 years it'll drop like 65%. And sooner or later it becomes all dead. And who is going to take care of the recycle of the batteries? You or some company? No one tells us the answer yet. Because, well, when government encourage people to use the EV cars, I'm not sure whether they are ready for this kind of things to come conversation, because it will take a lot of effort and energy to decompose the battery material back to where they were, and then recycle it. It's highly impossible, very expensive. Anyway, just let you know, okay? So let's go back to what we were supposed to do in the class, the lemma cell. So for your research, because every one of you want to go to graduate school so that you can get a master's degree to go to the industry. And after you go to the graduate school, you are asked to do some research. Okay, if you go to the IT design, then there are two main directions of the research. High speed or low power. Okay, high speed or low power. So we are going to get to know what the lemma model is. All right, this is something that I asked you to do in your first, maybe the second homework assignment. Better is that. See, that's what I meant. All right, okay. We have a better one. The light is green, that means it is better. All right, this is what we are supposed to understand. So this is the inverter. This is the inverter. I would say the timing diagram of the inverter, all right? So let's assume we have a pulse, like the one on the top. It's called the V in. So for an inverter, okay, this is a rising edge, this is a falling edge. And if the inverter function is correct, we are going to see this response. Okay, the response is totally opposite to the original signal. So the low will go to high, high will go to low, and so on and so forth. And how to define the delay? Because this edge, okay, is corresponding to the rising edge over there. So we define the delay. It's called the propagation delay. It's half of this voltage, half of the VOL and the VOH, to half of the VOL and the VOH here. This is called the PHL. P stands for propagation delay. Okay, high to low. This is high to low. This is stands for the edge, P high to low. And similarly, we are going to have a propagation low to high. So it's a 50% to 50%. Okay, that's the definition of a propagation delay. Then for the rise delay and the fall delay, this is specially defined for the output signal. So for the fall delay, it's 90% of the high drops to 10%, and the delay here. Okay, it's nothing to do with the input. Okay, it's nothing to do with the inputs. And for the rise delay, it defines, reversely, okay, from 10% to 90% over here. So we have two delays, propagation delays and the transition delay. Propagation delay, there are two types of them, high to low or low to high. And for the transition delays, we have high to falling edge and the rising edge. Okay, this is a definition of delays, which you have done already. Okay, so what is a delay model? Remember that we have already got the numbers of the equivalent resistance and capacitance. So it's quite easy. See, this is how you do the estimation. You're going to love it, all right? Let's assume we have a very big load. Remember the load I gave to you? I assigned a homework is 0.1 watt pico-F, right? And check the number over here. This is a parasecond number. What is the unit over here? It's a femtofarad. It's 1,000 times of difference. So they can be ignored. You see my point? The load I gave you in the homework assignment is 1 pico-F or 0.1, okay, pico-F. And this is femtofarad, okay? It's 1,000 times smaller. So if you add the load over there, then certainly you are going to ignore all the parasitic capacitance over here. The only thing you have to worry is the resistance. That is why I asked you to add the load, because that is the main pole. That is a major factor, major delay. Okay, major problem of the delay. That's a C load because it's big. Okay, so now let's check this out. Okay, how fast the charging is? The current comes from the sky, from the VDD, and assume of course this is closed. Then we are going to charge everything here. Charge the capacitor to the limit about the VDD. Okay, then that this way. And for the blue line, okay, when the top transistor is closed, so the second one is on, we're going to discharge everything on the capacitor. And this is for this one. Okay, TPHL. All right, and these are two equations. You're going to love it. It's very easy. And they already, it my belief that when you are a sophomore, the professors teaching the circuit theory should have told you that this is a second order equation, R and C. This is a time, okay, and RC become the time constant. We call that a delay constant. That's fine. It's time constant. So this is for charging, RPCL. And this is for discharging, okay, RNCL. And we take 50% of the point where they are. You're going to love it. It's 70%. Zero, it can be derived. Plug in the numbers. 0.69. I always remember 0.7. It's easier. 0.7 RC. That is the propagation delay. 0.7, or you like it, if you like it, you can remember that 0.69. So as long as we can estimate the RNC, we can estimate the delay. Propagation delay is about the RC times 70%. That is a delay. So everything can be pre-estimated or pre-computed. Is that cool? Okay. Not that hard, huh? Am I too slow? Okay, now the next problem is, how do we define high or low? How do we define it? How to define high or low? Okay, there are millions of ways to define what is the voltage, okay, as high. What is the voltage for low? Okay, I'll give you this example. And this is a widely accepted standard to judge whether the signal is high or low. So let's assume this way. We have two inverters. They are cascaded together. And we are going to send a signal from left to right. So if we send a high over there, in the middle it becomes low. Okay, let's assume that inverter works properly. Then we are going to have a high back. That's logically thinking. But we are electrical engineering designers as well. So we are not like information or digital or science guys. We have to get to the real thing. See, let's assume we have a threshold. And this is a VDD, this is a ground, of course. So everything, every voltage above this threshold, we assume, we consider that is 1. All right? And this is logical low. Everything below this line, we call this is low. And how do we define this? Okay, these are two thresholds. If we can send a signal higher than this one, this signal can be recognized by the follower, the second inverter, to correctly recognize it is high. Is that understood? Okay, so that's a logic high output range. Let me repeat again. This guy sent out a signal. Okay, if it's higher than this one, the second guy has to know that this is high. Okay, if it is below this one, this guy may misunderstand the signal. Okay, and all the signals below this line, the second inverter must recognize this is low. And this is a very special voltage over here we call VOH, output high. This is output low. So the first inverter got to have the capability to deliver a signal over this one or under this one, make it clear. And the second guy must have a very generous way to accept the signal. He said, okay, I'll give you some margin to do the job. So if you can give me a signal higher than this one, okay, I will assume this is logic 1. Lower than this one, because this is logic low. Okay, this is called input high and input low. Okay, so you might be a little bit confused. Okay, don't panic. And this stands for the capability for any inverter to send out a signal clean and clear enough. And this capability stands for the inverter when it is used as a receiver. He has to have a capability to recognize, make a differentiation of high or low. And output high and input high, the difference between these two voltages is called the noise margin. Noise margin. The bigger the noise margin, the better. Because that means the inverter that we design is capable of send a very clear signal, high or low. Okay? In the meantime, we can recognize the signal no matter how bad you are, I still can know what you are trying to say. Okay? So this one and this one, okay, it's called noise margin. The larger, the better. Okay? The larger, the better. All right? So this is how we do it. So how do we define the logic levels? It's over here. It's quite easy. This is the inverter. And you have a size ratio beta P over beta A. we define. Not hard. We take a derivative because it's unlike those square waves in the textbook. For the real inverter timing response, it is continuous signal. There is no discontinuity. So when the slope hits -1, there are two turning points here. When the slope, okay, shows you the 45 degree in this direction, that's slope of -1. Then the first one we run into, we call it the output high. And the second turning point, we call that the output low. This is how we make a definition of the unit gain points. And this is where the voltage high is and where the voltage low is. All right? So this is how we make a definition. So we maximize the noise margin, and this is how we select, okay? So in our design, for everybody design, this one, the higher the better. This one, the lower the better. That means we are going to have a very nice, okay, transition curve, close to perfect. Close to perfect. Okay, this is the logic levels. Okay, so now we're going to, integrate more circuits together. So this is what happened in your circuits. For everybody's circuit, this is design. You are going to have a driver, okay? You are going to have a lot of load. These loads might not be pure capacitor. They could be the input of other gates, very likely, okay? For example, your AND gate might be used to drive another OR gate, like the example that we showed you before, okay? So gate after gate after gate, okay, that's how the logic function is composed. So for the driver and the load here, there are a total of 3 types of capacitance. Okay, if you look from the viewpoint of the driver. The first one is the load created by itself, because we already know that any transistor has its own parasitic capacitor. That's one thing. We call that the self-load. The second thing, we understand that according to our introduction, every metal is over the substrate. So the metal and the substrate, there are 2 conductors. So of course they have wire load over there. And since we use a gate, use a lot of a gate, this here is inverters. If you look into the input of the gate capacitance become another load. So we have 1, 2, 3. And the C load usually is a combination of these 2. But a lot of textbooks, a lot of circuit design, they always ignore this part. They assume the metal is perfect. But in fact, it's not. Okay? Or you got to make sure that the load generated or equivalent to those gates is much, much larger than the wire load. Then you can take away this part without nobody gets hurt. All right? So basically, the load capacitance of logic circuits can be composed of a self-loading cap, and the interconnection or wire cap, and the fan-out cap. That is the capacitance composed of a lot of gates to be driven. So how do we do that? Okay, we look into all of them one by one. So the first one we run into is the load created by myself, by the driver. So how many capacitor here? See, you'll feel dizzy. It's like a maze. Don't panic. Don't worry. Okay, this is overlap created by this PMOS. These are 2 overlaps created by this MOS. And the overlaps over here can be decomposed into 2 parts. Follow the Miller theorem. If you don't understand the Miller theorem, please go back to your the sophomore textbook. Basically, any capacitor who both ends, they are not either shorted to the power or shorted to the ground, they can be cut into half and double it, and the input side and output side. This is what the Miller theorem says. Okay, if you don't understand it, go back to your textbook to find it. So we cut it. This is the equivalent circuits. Okay, you double it, put it over here, and double it, put it over here. All right, and self-load based on this decomposition. This is what you get. Okay, so C parasitic equal to these two. It's width of the NMOS, width of the PMOS. It's Cj plus 2 times the C overlap. It's about this big. About this big. Not too hard. Okay? So basically, but this is small compared to the load that you want to drive. Interconnect the wire load, the wire capacitance. If it's a short wires, that means it's only a few microns, so you can ignore that. But however, if the wire is very, very long, okay, larger than a few microns, you got to follow this lumped wire capacitance analysis. This one can be found in your sophomore year textbook as well. So, as we said before, if they are widely spaced wires, you can use 0.1 femtofarad per micrometer. If it's very tightly separated, as a 0.15. Okay, very long wires. This is called the distributed RC effect. Okay, so it depends on how long the your wire is. That is why I ask you to do one thing: make sure that all interconnection as short as possible. Don't use long wires. Otherwise, you're going to create delay problems. The last thing is fan out. Fan out is those gates to be driven. Okay, so this is how we look into an inverter. See, this is a gate capacitance. This is what you see over here. Gate capacitance. This is a big one. Okay, big one. So basically, the gate capacitance is equivalent to the summation of these two, CGP and the CGN. This is how you look into that. So the CG times the size of these two, and CG equal to the C oxide times the length plus 3 open overlapped is about this size. And basically, this one is small. Overlap usually is very small. So this is what you should remember: oxide times L, the big one, over there. So plug this, take this one into it. So you're going to find out it's equal to C oxide times L times WM plus WP. So basically, you count the area of this transistor. That's good enough. That's good enough. All right. So right now, we already analyzed these three major factors. So we put down all the numbers that you should know. So you don't have to remember all the numbers. This is something you have to remember. It's over here, the 0.18. Okay, 0.18. So this is a CGS, CG over here, 3.4. 3.4, this is the one you remember. And this is for parameters, 3.68. And C oxide, 1.33. Okay, you can do the same for every other different device process. But in this course, this is what you should learn is 0.18. Okay, so let's stop here, and because here's our here, we're going to take like a 10 minutes break.